Hi everyone! In Chapter 5, we learn about higher order linear differential equation with constant coefficients. So today, let's talk about the applications of those. So 5.4, mechanical vibrations. Most famous and classic application is mass on a spring, the spring mass system. So consider a mass attached to the lower end of a spring that itself is vertically suspended from a fixed point. So here we have the spring, and let's say we have a mass attached to the spring. What happened? It's gonna stretch the spring, right? Let's say the distance it stretched the spring is at 0. Okay, and how many force acting on this mass, this object? We have the gravitational force. The gravitational force is pointing down because that's the attraction of the Earth, right? And gravitational force, we know that equals to mg. All right, and by Hooke's law, the restoring force Fs is negative ky. So here, if we set the downward is the positive direction, then the restoring force is like the force from the spring force. Okay, it's gonna be opposite direction. So that's why Fs in this case is minus k. Y is how much we stretch the spring, right? In this case, we stretch as 0. So far, so good, everybody. So that's why at equilibrium position, which means the net force is 0. So we have the gravitational force plus the spring force is 0. That's net force is 0. Okay, and then that's why we get mg minus k as 0 equals to 0. So that means mg equals to k as 0. So we can usually solve k using the m and as 0, right? So k equals to mg over as 0 is how much we stretch the spring. Okay. All right. Now, if we apply a force to it, okay, so we'll apply a force to it and then stretch it and release. Well, the force acting on the spring include the restoring force, the spring force, resistive force, the damping force that is proportional to the velocity, which is negative CV, and probably an external force F of t. Okay, then let's look at this picture. So the spring force, we have the spring force going up. Okay, so that is F of s. Let's say this is y, so this is minus ky. Okay, and we also have the by the way, you can see let's say this force Fs is let's use a different notation. Let's use prime. Okay, or maybe S2, okay, because the mg, the gravitational force, already cancel with the spring force of the k times S0. Okay, so right now we have the external force. And when the object is moving, we have the resistance, right? Maybe air resistance or water or liquid resistance force. Okay, and that's why we call them damping force, and it's in the opposite direction of the object moving. So in this case, let's say it's this one. So we have the damping force F D. Okay, then this is negative c times v. So far, so good, everybody. Okay, so then here at equilibrium, by Newton's law, we note the net force equals to ma. So the net force equals to ma, and what other force? We have the spring force, we have the damping force, and we have the external force. So MA equals to negative KY minus CV plus F of T. Well, when we move these to the left-hand side, we get MA plus CV plus KY equals F of T. Wow, do you remember what is A? A is the second derivative, acceleration, right? Velocity is the derivative. So when we plug in it, then we get this guy. Wow, this is exactly second order linear ODE with constant coefficients. Okay? So if there is no external force, we get free damped motion. So no external force, so F of T is 0, so we get homogeneous. So this is a homogeneous linear ODE. Okay, and if there's no external force and damping force, we get free undamped motion, then the C is also 0, so you just get this guy. Okay, so remember when we have linear ODE with constant coefficients, we solve the characteristic equation, right? So this characteristic equation is AR squared plus BR plus C equal to 0. And then the roots, depending on the number of the real roots, we have 3 cases. If we have 2 real roots, let's say they're R1 and R2, then our solution is in the form of C1 e to the R1x plus C2 e to the R2x. If we have 1 repeated root, let's say it's R1, okay, then our solution is C1 e to the R1x plus C2x e to the R1x. If we have 2 complex conjugate roots, let's say they are alpha plus or minus beta I, then the solution is we can call them C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. So far so good. Do you remember all of this? Okay. So let's talk about the easiest, free undamped motion. So in this case, it means the C, the damping force, C is the damping constant. Okay, the damping force is 0 and the external force is 0. Okay, so we only have M y double prime plus ky equals to 0. Okay, so you can see we both divided by both sides by m. Then we get y double prime plus k over m times y equals to 0. So this is the standard form. Now let's let omega 0 to be the square root of k over m. Then we can get y double prime plus omega 0 square y equals to 0. Then the characteristic equation is y double prime associated with r squared and y associated with the constant term. So r squared plus omega 0 squared equal to 0. When you solve for it, you get r squared equals to minus omega squared. When you solve for r, plus or minus square root of negative omega squared. So because omega 0 is positive, we just get plus or minus omega 0i. Okay, so we have 2 complex roots. So if we're in the free undamped motion, we will have 2 complex roots. Okay, so and you can see here we have no real parts, only imaginary parts. So that's why our solution, our general solution, looks like a cosine omega 0t plus b sine omega 0t. You might ask, why don't we use C1 and C2? Well, let's use A and B because C1 and C2 sometimes if you don't write the letters so clearly, then it's kind of confusing, right? So let's use A and B so to distinguish them. Okay, so it turns out that we can write A cosine omega 0t plus B sine omega 0t as C times omega 0t minus alpha. Why is that? Okay, let me show you. So here we need a formula. Okay, so we need a formula here. So cosine alpha minus beta, that is cosine alpha cosine beta plus sine alpha sine beta. So far so good, everybody? By the way, cosine alpha minus beta is the same as cosine beta minus alpha. So far so good, because cosine, what's the picture of cosine? Cosine is symmetric about the y-axis. Alright, so cosine minus x is the same as cosine x. It's an even function. Okay, cosine is an even function. Okay, now let's see. Now let alpha be the omega 0t. Okay, so apply this formula, we will get so we will get here cosine omega 0t minus alpha, that equals to cosine alpha cosine omega 0t plus sine alpha, and we have sine omega 0t. So far so good, everybody? Okay, so when we multiply by c, what happens? So we have c here, and c there. Okay, now let's compare. So let's compare. Well, it looks like A is A cosine alpha, and the B is C sine alpha. So A is C cosine alpha, and B is C sine alpha. Then what is C? Well, you know that C squared is A squared plus B squared. Why is that? Well, A is A squared is then C squared cosine alpha squared. B squared is C squared sine alpha squared. And you can factor out the C squared, you get cosine alpha squared plus sine alpha, that's alpha squared. That is 1, right? So c squared times 1 is c squared. So that's why when we solve for c, c is square roots of a squared plus b squared. Okay? And what is the omega 0? So omega 0 is called the circular frequency. Okay? Is the roots of the characteristic equation. And what is alpha? Well, alpha, how do we solve for alpha? We can use, let's look at B over A. What's B over A? B is C sine alpha. A is C cosine alpha. C cancel. Sine alpha over cosine alpha is tangent alpha. Right? So alpha is then arctangent of B over A, but you have to be careful because the arctangent, the range is only covers minus pi over 2 to pi over 2, but your points can be in one of the 4 quadrants of the xy plane. So that's why here, depending on the picture. So let's say A and B, okay? So this is the first quadrant. So if A and B, so let's plot the points A, B here. So if A and B are both positive, then alpha is between 0 and pi over 2. So that's why it's in the range of arctangent. So alpha is arctangent of B over A. Okay, but if the point is in the second or the third quadrant, well then your alpha will be in the second quadrant means it lies between pi over 2 to pi. In the third quadrant means it lies between pi to 3 pi over 2. Okay, so when you apply arctangent, you only get the angle between minus pi over 2 to pi over 2. So you need to add a pi to it to make it into the second or the third quadrant. Okay, so that's why if the point is in the second and third quadrant, it means your A is like the x-coordinate, your A is negative. Okay, if your B is positive, then you're in the second quadrant. So second quadrant is when B is positive, third quadrant is when B is negative. So both A and B are negative, then the point is in the third quadrant. Then angle alpha equals to pi plus arctangent of B over A. In the fourth quadrant, you can still use arctangent of B over A, so then the angle is between minus pi over 2 to 0. But sometimes people want the angle to be positive, so that's why they added 2 pi to it. So far, so good. So see, an angle here is from minus pi over 2 to 0, but when you add 2 pi to it, you can make the angle positive. So that's why this is a formula about the alpha. It really depends on the sign of A and B. Are they both positive? Then we're in the first quadrant. If the A is negative, then we're in the second or third quadrant. If A is positive, B is negative, then we're in the fourth quadrant. Okay, so such motion is called simple harmonic motion. And why is simple harmonic motion? You can see C times cosine is oscillating. Okay, the period, which is the time required for the system to complete one full oscillation. Well, remember we look at the coefficient of your t, okay? So the period is 2 pi over the coefficient of t in your cosine. Okay, so this is the formula of the period. How about the frequency? The frequency is nu equals to 1 over the period, so it's omega 0 over 2 pi. Okay, so this is not v, this is nu, Greek letter, nu, okay? We can also express the solution as, so now so after you figure out A and B, you can find C. C is square root of A squared plus B squared. And then you can find alpha. Alpha is one of these formula. Okay? And then you can factor out omega 0. When you factor out omega 0, you get T minus alpha over omega 0. And let's call this guy delta. Then delta is the time lag. What's the time lag? Well, you know cosine. Cosine looks like this, right? So this is cosine x, right? And this is 1. This is minus 1. This is pi. This is 2 pi. And this is like pi over 2. This is 3 pi over 2. This is the picture of cosine. And when you multiply by c, what does the c do to this function? It stretch. It's stretched vertically by a factor of c, right? So we still have the same picture, but now it starts with c and here minus c, so we still have here, so we still have this picture. Let me draw it better. Okay. Okay. Good enough. Okay. So this is still 2 pi. This is pi. So this is c times cosine x. It stretched the curve vertically by a factor of c. And then what happened here? The omega 0 talk about whether we compress or stretch in the t-axis direction. Okay. And then next we have the let me see. And what do so the time lag delta? The delta is like we shift the curve to the right delta units. So this is how much we shifted. Okay, how many units we shifted. So far so good. Okay. So this is like how much we shift to the right. Okay, delta units. Okay. So far, so good, everybody. Let's work on example 1. A body with mass 1/2 kilograms is attached to the end of a spring that is stretched 2 meters by a force of 100 Newton. It is set in motion with initial position y0 equals to 1 meters and initial velocity is -5 meters per second. Find the position function of the body as well as the amplitude, frequency, period of oscillation, and the time lag of its motion. Okay, so let's draw some picture. So this is a spring, right? We stretch it and then it bounces off. Okay, so mass is 1/2. Okay, let's put down the information, kilogram, and the force equals to K times S0, right? But here we know that the force is the okay, so a body with the mass is attached to the end of spring that stretched 2 meters by a force of 100 Newton. So 100 Newton can stretch it by 2 meters. Okay, so here we can solve for K. K is then 100 over 2, which is 50. So far, so good. And we are also given that the initial velocity is 1 and the initial position is 1. Initial velocity is -5. Okay, so what is our formula? Because we're in the free undamped motion, so the formula is my prime prime plus ky equals to 0. Okay, so let's plug in the numbers. M. Okay, so M is 1/2 y prime prime and K is 50. So let's make the coefficient of y prime prime to be 1. So let's multiply by 2 on both sides. So that's y prime prime plus 100y equals to 0. So this is the linear differential equation with constant coefficients. Okay, so what is the characteristic equation? Well, the characteristic equation is r squared plus 100. Don't put the r here. R corresponds to y prime. Okay, so y corresponds to the constant term. Okay, how do we solve for r? Well, we move the 100 to the other side, and then the r is going to be plus or minus 10i. We have 2 complex roots. That's always the case when we have a free undamped motion. Okay, because we have 2 complex roots, the solution looks like a cosine 10t plus b sine 10t. So far, so good, everybody? Okay, so we have to figure out A and B. How do we figure out A and B? Well, we have the initial condition to figure out. So when we plug in 0, we get 1 is y0. Cosine 0 is 1. Sine 0 is 0. Oh, so A is 1. That's correct. How about velocity? We need to plug in, we need to find the derivative. Okay, so derivative of cosine is minus sine, but there is a chain root. You need to multiply by 10. And then derivative of sine is cosine, but there is a chain root, so you also need to multiply by 10. Alright, then we can plug in y prime of 0, which is the velocity. That equals to sine 0 is 0, cosine 0 is 1, so 10b equals to minus 5. Then b is minus 5 over 10, so minus 1/2. You see, we figure out A and B. Now, we remember our formula. We want to express y in terms of c cosine omega. So our omega 0 is tan t minus alpha. So this is what we want to express the solution look like. Okay. Then what is c? Well, c is square root of a squared plus b squared. A squared, 1 squared, right? B squared is negative 1/2 squared. Okay, so that is 1 plus 1 over 4 equals to, what is that? 5 over 4. And then we have square root of 5 over, what is square root of 4? Yes, that's 2. So this is the amplitude, okay? This is the amplitude C. Okay, so next, frequency. What's frequency? So frequency is nu. Nu is 1 over the period, okay? So period is 2 pi over omega 0, which is the coefficient of the t in the cosine, which is 10. So that is pi over 5. Then the frequency is the reciprocal of the period. So that is 5 over pi. So far, so good. And next, what is alpha? Well, alpha, we have 3 formula. It really depends on which quadrant we lies in. So A is 1. 1 is like here, 1, right? Negative 1/2. Oh, like there. So negative 1/2 and 1. Let me draw it bigger. So this is the point. Okay? So you can see it's in the 4th quadrant. Okay, so 4th quadrant. So our formula is then 2 pi plus arctangent of b over a. B over a is, okay, let me do it slowly. B, what is b? Minus 1/2. A is 1, so minus 1/2 over 1 is minus 1/2. Okay, so far so good, everybody. And so this is the alpha. Okay, so you can plug this number in your calculator. Okay, so make sure when you plug it in, we're in the radian mode, okay? So let's see. Yeah, because this is radian. If you use the degree mode, you're gonna use your degree at the 2 pi. It won't work. So make sure you're in the radian mode. Okay, and then 2 pi plus arctangent of negative 1 over 2. Okay, I got this approximately by 5.8195 radian. Okay, so then the time lag, delta is alpha over omega 0, so which is 5.8195 divided by 10. Okay, so then we get 0.58195. Okay, so that is the time lag. Their angle, the units is radian. So far, so good. So if I want to rewrite my solution is C. C is square root of 5 over 2 cosine 10 t minus alpha. Alpha is 5.8195. So far, so good, everybody? Okay, so this is the first example. Let's continue. What happens if we have free damped motion? Okay, which means free damped motion. Free means f of t is 0 on the right hand side. Okay, damped means we have damping force. So c is not 0. So we have a middle term here. Okay. So so we're gonna divide both sides by m. Then we have y prime prime plus c over m times y prime plus k over m times y equal to 0. Okay. So here okay. So here because it's easier to use the notation, so we let omega 0 be the square root of k over m and p equals c over 2m. Why do we do that? Okay, that is because just looking at this, what's the corresponding characteristic equation? Well, it's r squared plus cmr plus k over m equal to 0, right? When you solve for the roots, well, the root is 2a, which is 2, plus or minus, 2a and then the negative b, so negative c over m, plus or minus b squared, so b squared, which is c squared, m squared, minus 4ac, a is 1, c is k over m. So far, so good. Okay, so let's simplify. Let's multiply by m in the numerator and denominator. Then what happened? We have m and m cancel, so we have the c, right? So negative c on top. Here, we move the m inside the square roots, it becomes m squared. So we're multiplying each term in the square root by m squared. So then the first term becomes c squared. The second term, you multiply by m squared, so the m in the denominator cancel one copy of the m. We still have 4km over 2m. So far, so good, everybody. So that's why if people make the change of the variable, they will get, let me see. Yes, so that if they let p to be c over 2m, they can split. So you can see when I split it, I get c over 2m, and then we have plus or minus. Well, when we move everything to the square root, so we have c squared minus 4km and over 4m squared. Okay, so this guy is the real part. So the real part. Okay, and this guy is the imaginary part. It really depends on whether the number of roots. Okay, so this guy is gonna affect whether we have two real roots or one repeated root or two complex roots. Okay. All right. So we get three cases. First, overdamped case. Well, that's the case when we have two real roots. Okay, suppose we have two real roots, R1 and R2. By the way, you don't need to memorize this formula. Okay, you don't need to memorize this formula. It's just when we solve the differential equation, we get the roots, and then we look at the roots. If it's two real roots, then we know the solution looks like this. Okay, so don't need to memorize this formula. Okay, we don't need to. Okay, so when we have two real roots, you will realize both of them are negative. Okay, then the position functions has this form. When t goes to infinity, because all the r1 and r2 are negative, we know exponential function. If the exponent is negative, so this is like e to the minus x. When x goes to infinity, then it goes to 0. So that's why the body settles to its equilibrium position without any oscillation. Okay? So second case, critical damped case. That is when we have one repeated real root. Okay, then the general solution, let's call the root is negative p. Well, then the general solution looks like, because it's c1 e to the rt plus c to t e to the rt. When you factor out e to the rt, you get c1 plus c2t. Okay, so here the r is also negative, so we still have going down, but because the c1 plus c2t is a linear function, okay, it might equals to 0 at some point. So your picture, this is without the linear factor. With the linear factor, you might have something like this. You might you might cross not so good. You might cross it, or like that, cross the t as ones. Okay. Yes, when you find the t coordinate, this guy is always positive. This guy, when you set equal to 0, you get c1 plus c2t is 0. Then t is negative c1 over c2. Well, depending on the c1 and c2, if this number is positive, then it cross it once. Okay? So that means the body passes through its equilibrium position at most once. Okay, and the 3 is the underdamped case. That's the case when we have two complex roots. So two complex roots, so let's don't use alpha and beta, because we use the alpha to be the angle of the time lag, how much we shift the function. Okay, so let's use other notation. Let's use omega 1. So let the roots be minus p plus or minus omega 1i. Okay. Okay, so let this be our root. Then our solution looks like e to the minus beta t, and then a cosine beta omega 1t plus b sine omega 1t. So omega 1 is the real parts. Imaginary parts. Negative p is the real parts. So what's the picture looks like? Well, we know this guy exponential function looks like that, right? But now we have a little bit oscillation. So it oscillates. So this is a picture what it looks like. Okay, so that's why this is called underdamped case. The damping force is not so strong. We still have oscillation. Overdamped case, the damping force is so strong. We don't have any oscillation. Okay, so the body settled to its equilibrium position without any oscillation. Critical damped case, we might cross it once, okay, but at most once, might be 0. Okay, well, if we're in the third case, underdamped case, okay, then we have omega 1. Then you can express your solutions in terms of, so now look at this part. We can express as c times cosine omega 1t minus alpha. Just like what we did before. C is square root of a squared plus b squared. But now our amplitude is not only c, but also c times the e to the minus pt. So this together is the time varying amplitude. Time varying because it's a function of t. It's not a constant anymore. Unlike the free undamped motion, we have a constant amplitude. Here with the damping force, we have a time varying amplitude. Okay? All right, and omega 1 is called the pseudo frequency. Okay, this is pseudo frequency. And how to figure out alpha? Well, the way how we figure alpha is exactly the same as before, depending on the values A and B and which quadrants the point lies in. If it's in the first quadrant, then it's arctangent of B over A. If it's the second or third quadrants, then it's pi plus arctangent of B over A. If it's in the fourth quadrant, then we have 2 pi plus arctangent of B over A. And then here, T1, we use T1 to distinguish the free undamped case, right? Okay, so T1 is 2 pi over omega 1 is the pseudo period of oscillation. Okay. And in general, omega 1 less than omega 0, T1 greater than T. We can also express our solution as, so we can factor out omega 1, then we have T minus alpha times divided by omega 1. Then this is our time lag. Okay, so the way how we find it is very similar as the way we did before. So far, so good, everybody? Okay. So this is the combined graph of it. You can see the pink line is the strong damping. You can see it just go down, approaching to 0. So this is over damped case. Okay, we have a strong damping force. We don't see any oscillation. Okay, the green line is the critically damped case. We might cross, so you might cross the axis. Cross the t-axis once and then you're approaching to 0 after it. So we might cross it once. That's critically damped. And do you see the red line? The red curve is the under damped case. So we are bounded between the by the way, let me write it down here. So this upper curve is e to the minus pt. Okay, and this lower curve is negative e to the minus pt. And then, so you can see the red curve is oscillating between them. Okay, so it's still going to 0 when t goes to infinity. And do you see the blue curve? The blue curve is undamped. So if it's undamped, then the amplitude will be the constant. See? The amplitude here is C. That's constant. That's the undamped case. Well, imagine, so we have the spring and mass. If you put it in like a water, there will be a more damping force. Then it will oscillate slower, not as far as before. Okay, and eventually it will stop there. Okay, everybody. All right, so let's work on some examples. Okay, let's continue this in video part B.